Hi everyone, we're going to be we're doing another review of C++ or C for our work that we did in BIT 1400. So let me get going on that. So let's look at what we would do in the past. So just as a quick reminder, uh, I like maybe I'm overcompensating, but I like always pointing out the fact that there's this weird dichotomy that you get with programmers, where you flog yourself about how terrible you are. Oh my God, I can't do it. Or a lot of students do that. I know I do that. I'm no good. I suck. And then everyone else around you goes, "Oh, that's beautiful," or "That's really well done. Look at that beautiful code." And then when you get down here, you notice you know every single fault, every single problem in your code. That's actually a good attitude to have. Some people that are overly, arrogant or overly confident about their work don't see the problems in their code. And that's even worse than being overly critical. So it's okay to be critical about your code. Just be aware that it doesn't necessarily mean that other people see all the faults in your code. Much like writers have the same problem, where every single sentence that they write, they could have made that sentence better, but other people don't notice that problem. So we're going to do an extended cut of the C review. Why? Because way back in the day, I did this really brisk, rampage through C code, and then everyone was still confused. So I want to make sure that you are comfortable with this. If you are completely comfortable with C, and this is up to you to whether you know it or not, then sure, you can skip ahead. I will say if you were the least bit uncomfortable, I would strongly recommend a review. Why not? It's faster than, trying to find out the hard way later on that you don't actually remember C. If you did not take the course with me, 1400, I strongly recommend listening because I know that they did not do pointers and other things like that to the same extent that I did in my class. Okay, so we're going to do a review of C. I'm going to start writing up some C. Let's do hopefully the program that we did last time around, maybe find primes. Um, so we're going to write a C program. I'm going to make a new project just to review that. Uh, and hopefully we'll have our first real quiz, which I still have to open up, of course. So let's jump into this. In case you're wondering, C is a fairly old language, 1972. By the way, one of the recommended textbooks is done by Dennis Ritchie. They did it for Unix. So way back in the day, there's been three different versions of C that have come out after that. ANSI C, ISO C, and C99 all came out after 1972. These are updates of it, if you will. A service pack, if you will. Refinements of the C language. But in 1983, this idea of object-oriented programming came around. It's been around for a little while. It was in academia, and then someone finally decided to put that into C because C was such a popular language. They wanted to have objects in C. So C++ is born. Now, C++, if I've already not already said this to you guys, is essentially bolting on object-oriented programming onto the C language. It is not designed from the ground up to be an object-oriented language. I mean, the language itself was built from the ground up, but it's backwards compatible with C. It's very much like a PlayStation 4. You can play a PlayStation 3 game. So a PlayStation 4, you can play PlayStation 3 games. You can also play PlayStation 4 games, right? It's backwards compatible. So C++ is backwards compatible with C, so you get this weird disconnect where you don't know where C ends and where C++ begins for a lot of programmers. More importantly, though, it means that there was a whole lot of compromises being made with the C++ language, where it wasn't designed from the ground up to be like that. It's because it has to match with C, and so you get some weird quirks along the way. We will hit some of those quirks when we do templated libraries and things along those lines. You'll hit situations where you go, why in the heck did that? Why does it look like that? And the answer is because it's C with something tacked on the side, right? We bolted on this object-oriented language part to C to give you C++. It is not as polished or nice looking as some other languages like Java was relatively well done. Rust right now is a big language that's coming up. There's a number of these languages that are Python that are really well designed languages that from the ground up have always been designed to be object oriented. Notice I did not say JavaScript because that is a piece of garbage language. Sorry, I love bashing JavaScript. My Viz class people know about that. Okay, so it is easily the most low level of the high level languages. In Python, you say do something and it does something, right? I'm making an array, I'm going to make it bigger, and under the hood, magic happens and the array gets bigger. C++, like C, involves, oh, I need to know where the memory is. I need to do memory management. I need to delete stuff when I'm done. I can move pointers around. I can do all this really crazy stuff. My arrays do not automatically adjust in size. My arrays don't have a size variable associated with them. I have to actually pass an array of the size of the array in my functions. Like, there's all sorts of things that we would never ever do nowadays. But the language, because it was invented in 1983, that is part of the language. And in case you're thinking, oh, well, why doesn't C just go away? Because it's so low level, because you have so much control over the minutia of the language, because you decide when to delete stuff. There are people that swear by C++. It is easily going to be the most efficient language. If you're doing a video game, you use C++. Or you might have some layer on top of C++, but it goes down to C++ because it is far faster in terms of computational speed and efficiency because you have so much control. So one of my former instructors once said, if you want to write it fast, you write it in Java. You want to write it correctly, you write it in C++. That's not always the case, but it's a nice way of looking at it. C++ will take you a lot of time. It's very verbose. You have to write a lot of code. You don't do it in one line, but it's powerful because of that control over the individual little details. It means you can do a lot of really impressive stuff. Okay, C Sharp also another language that comes from C and C++. Java, C Sharp, Rust, a lot of these languages, even JavaScript, all have a syntax that owes itself to C++. They look like C++ because C++ did it right the first time, essentially. Okay, so some of the ideas, constructs, and ideas, there's cross pollination. You you learn C++, you can figure out C Sharp on your own. So in case you thought this is just a waste of your time, no, all of these languages are using the same syntax. If I was doing some other crazy language, like Lisp, for example, doesn't come up that often. All right, so here is what we did, and this might be news for, excuse me, anyone that did on the course without me. If you're in 1400, this is old hat, right? You Compilation in C and in C++ is actually a three-part process. It's not one part, it's three. So, first part, first part is we have pre-compilation. We have these things like include statements, like defines, all these things with a hashtag in front of the pound sign in front are pre-compilation instructions, as in you will do that before you compile. It allows you to do find and replaces everywhere. It allows you to include other libraries, that sort of thing. The pre-compilation phase. That you haven't compiled any code. You're literally just taking chunks of code, stuffing it on top of your program. It is text find and replace, and it's being done without your being aware of it. Step number 2 is compilation. So we will take our C code, we will convert it down to an object file, which is essentially machine code. So we will go from human readable text. That's all this source file stuff here, source file 1.c. It's a text file. You can look at it in a text editor. There is nothing special about it. There's no special watermarks or anything like that. It's just a text file. But the compiler knows how to read it, how to deal with it, and will make something that the machine can use, this object file. But the object files don't know about all these other libraries. So we have this machine code, a bunch of chunks of machine code, but they're not hooked up. They're little islands of machine code, little chunks that are all independent. But if I include somebody else's library, I don't have that other person's library in my object file. That's somewhere else. Or if object file 1 needs object file 2, it doesn't know where that object file 2 is. And that's where the linker comes in. So I make machine code, and then at the end, I hook up all the various parts. Oh, you need to know about this file? Okay, I'll figure out where that is. Oh, you need to know where that thing is. Oh, it's over here. Think of it as hooking up all the individual parts. I make a bunch of Lego structures, and at the end, I hook them together to make the Death Star or the boat I'm making or whatever object I'm making. Right? It's the connecting parts. That's what the linking is all about. And at the end of the day, I have machine code that's executable. That's what the EXE stands for. That's if you know Java or some other languages, it might seem, I always thought it seemed like witchcraft. If you have Java, you can't just run their file. You have to run it in some kind of Java interpreter, right? Instead, in C and in C++, I will get an executable. I can double click it and it runs and it works. Period. That's one of the beautiful things about C and C++. If I make a game in C, I get an executable, I double click the executable, I'm done. It's working. And so it's a three-part process. I have pre-compilation, which is those hashtag things. I then have I have compilation, which I go from text files to machine code, and then I hook everything up with a linker. So I'm going to do a little bit of coding in Visual Studio. It's going to look like this, and we'll make a called test application or something like that. So let's find out. So let's do this. So I am going to make a new project. It's going to be an empty project. You might be tempted to do like the console application, which is a hello world. Please don't. Empty. The reason I do empty is because all these other ones, unless you need to use them, all these other approaches will add extra stuff in them. Windows in its infinite wisdom, or Microsoft in its infinite wisdom, keeps on shoehorning other stuff. It'll make predefined variables and the like. That's all well and good for you when you're trying to experiment or test something out. But if you want to share your code with somebody else, or you just want to pass on that file, now you have to pass on a whole bunch of other files. You can't just pass in that one C file and it works, or that one CPP file and it works. So we're going to next. I'm not going to put in my normal repos. I'm going to Sprague, and then I'm going to go to, as I said, it's all in my Google Drive. So I'm going to go to Carlton 2400, and then fall to 2020. Here is my in-class code. I got a bunch of in-class code in here, but so I'm just going to create it in here. And this is going to be lecture, let's say lecture, I have a linked list demo coming up. Lecture 2, I'm going to call lecture 2. I'm going to have to delete a lot of these. All right. And my project is L02 test code. And I hope that is not something that's private. Okay, create a new solution, and I'm going to create this. Hopefully, when it finally gets around to it. All right, we have nothing in it. There's nothing in this project at all. But notice I have a place for my source files, my CPP files. I have a place for my header files, which we'll get to later. They're just other text files. And we have resource files like images, like text files that we're going to use, that sort of thing. We can put those in there. So I'm going to add, and I'm going to make a new item, and it's going to be a CPP file, and I'm going to call this L02 find prime, min prime. Let's call it that, and we're going to add it. Nothing in it. Okay, so I'm going to int main. I'm going to close this off. Okay, what I want to do is I want to include certain things. So I might do include IO stream. I might include assert.h. What the heck is this stuff doing? This is going to find a file somewhere in my system. I have certain directories that it always goes to. I'm going to find a file called iostream.h. It's implied it's .h. And I'm going to take that entire file and shove it at the top of this program. I'm then going to take assert.h from my system and shove that file right on the top of the program. That is what this precompile header does. You never see this. You never see that code. but that's what it's going to do. It's going to take all whatever IO stream is, stuff it at the top of my file. Take assert.h, stuff it at the top of the file. You never see it because then it immediately becomes bytecode. It becomes assembled or machine code. Why do I want this? Well, I just wanted to show you a precompiled header. I'm also going to include prototypes. So let's put a prototype in here. Prototype, if I can spell. And so here's my prototype. What did I want it to do? We could do it unsigned int, or we can do it as an int. Let's do it as an int. So min prime, let's say, and then, or min factor. Min factor, I think is what we called it. All right. This is an IOU. This is saying, I will eventually get to this, but I will eventually define a function called min factor. Where is it going to be? It's going to be defined somewhere else, and I will link it up for you. So we're going to deal with that in a second. So the first thing I'm going to do is I'm going to make an int. Let's not even make an int on this one. Let's say factor 1 is equal to min factor, and then I'm going to put what did we try last time? 12, and factor 2 is equal to min factor, and we tried 7, and we said before we get going, we're going to we can make predictions, so we can say should be 2. Comment to myself, right? What I expect from this function to before I get going. Or I could do this. Assert factor 2 is equal to 7. And what the heck is that all about? For those of you that have never seen me do an assert before, an assert is, it always seems like crazy. It seems absolutely crazy. We are going to make our program blow up. Or more importantly, we are going to make, if something doesn't happen the way we expect it to, we make our program blow up. This is the exact opposite philosophy as JavaScript. JavaScript says, hey, we'll handle your errors and hopefully you'll get something going through. And so what happens is you program something, it sneaks on through, and then you release it to customers, and then the customers find the error. Right? Bad things happen later on when the customer finally gets it because you didn't solve the error right away. You waited and you waited because it's trying to gently or elegantly handle an error. Instead, the way of doing an assert for in C loves asserts, is you say, I'm going to assert that this is true, and if it's not true, blow up. The reason you want not literally blow up, but it stops your code dead in its tracks and crashes your program on purpose. Because if it crashes your program there, you know where the problem is. It's there, not 20 minutes later when the thing cascades and makes other problems later on. If you have a memory leak, you find the memory leak right away and you solve it right away. You allow you to test your code before you move on to the next part by putting in, I'm asserting that factor 2 should be 7, and if it's not 7, holy crap, stop. Stop everything. If I make stupid little typing errors, I'll catch them right away. And the most important part of asserts is if in debug mode, if I'm building my code with debug information, asserts work. And if I do it in release mode, debugs get removed. All of these asserts just go away. They're not even looked at. They're programmatically removed from my code, and they don't actually ever go to a customer. So it means the programmer finds the problem when they make a problem, but the customer at the end will never set off one of these asserts because they don't actually exist in the code anymore. And makes a huge difference. It means that the one person that can actually fix the problem fixes the problem, not the customer complaining about the problem and then you having to find out how to fix it 4 months later or 6 months later when you forgot what your code did. So this allows us, it's a very cheap and dirty way of testing code. Okay, so I have something called min factor. Notice it's perfectly happy. It says, hey, there's a function called min factor. I'm going to call it. The place where it says there's kind of warning is min factor hasn't been defined yet. But Because there's something, the prototype is up here, it knows that there's something called min factor, and my main method can call min factor. The fact that min factor hasn't been defined yet means I still owe you a function called min factor, but the program is always going top to bottom. It always goes top all the way to the bottom, and if there's something called min factor, there wasn't something called min factor beforehand. If I comment this out, boom, I have an error. It does not know min factor is defined. This says I owe you one function called min factor, and if you don't define it, then there's a problem, but it allows your program to know about functions you're going to be using. Otherwise, you need to worry about the order in which your functions are defined. So, prototypes are just a single line stubby saying, I owe you one function called min factor. And then later on, I'm going to go down, I just did a copy, and I'm going to go down and I'm going to define min factor. So, for right now, I can say return 0 or something like that, just to shut it up. Okay. So this is what I would expect. I've done my program. It's going to fail miserably. These asserts are going to go off. But let's compile it. Let's see what happens. It's going to compile. Notice I didn't compile and execute at the same time. I compiled, saw if there was any errors. Oh, it all passed. What are we going to see? When I run this, I'm going to get here. Factor 2 is going to be 0 because this thing returns 0. I call min factor of 12. We can actually, let's throw in a breakpoint. I go over to the side here. I press this. Or I could also press F9 to drop a breakpoint. F9, F9, F9. Okay. Or I can just click here. This will drop me in my program right there and I can go into it. So let's run this. I'm going to press the play button and see what happens. So I've compiled, then I run separately. I have now stopped my program exactly on this line. See the arrow? It's on this line. And I can see what everything is. I have a 12 coming in here. Min factor, I'm going to be calling it min factor. I want to step into min factor. So I can look at this, I step over, step into, step out. If I'm in a function, it steps out of the functions. If I'm here, I could just go to the next line. That's step over. I don't go into it. Step in will mean I walk into I walk into the min factor function. I'm going to step in. That's F11, by the way, for hotkey. Click that. I am now in. I jump down to min factor. I'm going to do min factor. And when I'm done with this, I'm going to go right back to what this was doing, right? It's a temporary, aside. Min factor, I jump down to min factor, and then I go back up again and keep working. Right? That's what a function is. It's a subroutine that I'm going to go over to, do that, and come back. So I'm now in min factor. I'm going to step over to go to the next line. Step over again. I'm going to return 0. And now if I keep on one more step, let's look at what factor 1 says. Factor 1, if I hover over it or if I look down here, the value is 0. By the way, notice what factor 2's value is. It's some ridiculously large negative value. Let's look at the hexadecimal version of it. Remember when we were learning C? Hopefully you guys, anyone that didn't do my class, has seen this, but as a hexadecimal number, it's C, 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 C. If you break that down into binary, what does it look like? It's 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. I think it's 0, 1. I'll have to double check. Right? Maybe it's 1, 1, 0, 0, 1, 1, 0, 0. In either case, I have a pattern. So I know if that variable has not been initialized yet. It allows me to know when I haven't touched that variable yet. Okay, so I don't want a hexadecimal value. And as an integer, that's interpreted as a huge negative number. Okay, so I'm going to do min factor again. I'm going to step over this. This time I'm not going to go into the function. Min factor of 2 is also equal to 0. And I'm saying factor 2 must be equal to 7, otherwise blow up. Okay, and blow up. I can abort and see what this actually says, or I can look at what's happening. I can retry, and that'll tell me where I am in the line. But if this statement is actually false, everything crashes on purpose. Now that everything's crashed, let's go and fix my code. So instead of here, I need to define this function. So I want to check to see, first of all, I got to think of my worst case scenarios like I did last time. My scenarios are the number I'm trying to factor is a negative number or 0 or 1. If it's any of those, well, bad things are going to happen. Okay, so let's do this. If 2 factor is less than 2, I'm going to just return 2 factor. Or I could return negative 1, for example, if I wanted to say that's an error. A factor should never be a negative number, perhaps. Whatever works for you. Let's do that. Negative 1, right? There's never going to be a negative factor, so this is a dummy value I can return. So you're trying to factor some negative value. Factoring doesn't work for negatives the same way. So let's say, and if you give me bad data, I return negative 1. You gave me bad data, I handle it elegantly, but the answer is not going to be right because there's no meaning of right. You gave me garbage, I give you garbage. Okay, next up, I want to do a for loop. I want to find out, and I can even test this by the way. So let's do assert min factor of negative of 1, and that's equal to negative 1. I could put in a bunch of tests to make sure that this thing is going to blow up in the way I expect. I expect it to blow up for, sorry, not negative. It's negative 1 still. I wanted the 0 here, and I want, let's say, a negative 3 here, right? I expect this thing to blow up, to give me a negative 1 in these kinds of cases. Sure, let's test it. Doesn't hurt to test it. I'm going to test my code with an assert. Okay, next I'm going to actually do what I'm supposed to do. I'm going to find the factors of 2 factor. So for int I is equal to 0, I is less than 2 factor, I plus plus, and then what's next? I need to figure out if if it's divisible by I. I don't want to start off at 0. I'm going to start off at 2. I got to check my code that I gave you guys as well, because it should never do 0 and 1. So I got to go back to my old code actually. I may have had a bug in the handwritten code that I did, right? What's going to happen if I do 0? It's going to have a divide by 0. It's going to crash. If I try 1, it's always going to be divisible by 1. That's not going to work. It's always going to say, yes, it's divisible. I have to start at 2 and move on. Okay, so so I'm going to fix the slides, but we'll point out what's wrong with the slides when I'll update the slides, but not necessarily the lecture. Important things when you fall on your face to just address that you fell on your face. So let's look at this. I'm going to start at 2. I'm going to go to the number I'm factoring. I could stop at halfway point or the square root of the number I'm trying to factor, but let's just go to 2 factor. I'm going to say if 2 factor is divisible by I, so I don't want divisible, I'm going to say remainder. If I have 2 factor, let's say 11, divided by 2, do I get a remainder? Yeah, I should. If it's equal to 0, it means it's evenly divisible, meaning it's a factor. And so I'm going to return, if I find a factor, so if evenly divisible, then I'm going to return I. I don't have an else condition here. Why? Because if it's not evenly divisible, I want to keep going. The keep going is just increase I, check the next one. Increase I, check the next one, keep going. Okay, and then when I'm finally done, when I've gotten to the end, it means if I get to the end, it means I never stopped in one of these places. Meaning, at the end of the day, after I've gone through all the numbers up to 2 factor, it means 2 factor must be a prime number. So I'm going to return 2 factor. Right? It's divisible by itself and 1. So if it's a prime number, I'm going to say the largest factor is itself. I could return 1 technically, I guess, but I want to return that. Okay, that should do it. Let's try it out. Let's compile it. Let's make sure it compiles. Hey, it compiles. Great. Let's run my program. I'm going to hit my assert. I'm going to step into my function. So I'm going to check 12. So I step into my function. I'm going to check to see if 12, so first up I'm going to is 12, so I can look at what 2 factor is. It's the value 12. Is 12 less than 2? No, it's not. I'm hoping we all agree on that. So I'm going to jump through that past that if statement. I'm going to keep on increasing I, starting at 2, and checking I is equal to 2, I is equal to 3, up until I find something that's a factor, or I get to the number that I'm looking for. Okay, so is 2 factored 12 mod 2, does that give you 0? It should. 12 is an even number. So it is 2 factor, so 12 divided by 2 is 6 with no remainder. So it should, this is a remainder, this should go right here, and then I'm just going to return the value 2. Factor 1 is equal to 2, right here. Great. Let's try the next one. Let's step into this one. So I'm going to the function again. This time 2 factor is the value 7. Okay, so if I'm going to, so the value 7 is greater than or equal to 2, so I'm not going to go into there. I'm going to keep on checking numbers from 2 up to 7. So next, is it evenly divisible? No, it's not. Next, is 7 divisible by 3? No, it's not. Or evenly divisible by 3? No, it's not. Is 7 evenly divisible by 4? No, it's not. Keep going. How about 5? No. How about 6? No. Now the I value is equal to 7, and I jump out of my for loop because I keep going until this I is less, as long as this I is less than 7, I'll keep going. Well, I is equal to 7 now. So I can go down here and I can just return 2 factor, the 7. Okay. I'm now factor 2 is equal to 7. Factor 1 is equal to 2. Great. So I can check to see if, let's find out what this thing does now. Min factor, hey, that passed, that passed, that passed. Factor 2 is equal to 7, that passed, that passed. Great. My program is finished. I'm going to do one more thing because I forgot. Notice my main method has to return something. I'm going to return 0. This is just by convention, by the way, in case you're wondering. You could have void main or int main. Some people swear that you should never have a function that returns nothing. So in this case, it returns 0 if everything's a-okay. Otherwise, it returns some kind of maybe some error message or some like some number that represents an error. Okay, but that's my function. I can check a bunch of different numbers. Let's try one more number. Let's try, I would normally ask you guys for this, let's say 21. Okay, and factor 3, I would expect factor 3 to be equal to 3. Maybe I should 25. Let's try 25. I want something that's going to not work very well. Or it's going to work, but it's not. And notice it's easy to screw up my typing. That's why I make sure I have asserts everywhere. Right? Syntax errors are common. So factor 3, I expect it to be 5 because 25, the factorization of 25 is 5 times 5, right? That's the smallest number. Those are the prime factors. So factor 3 should be 5. That's the smallest factor of 25. Great. And I can actually just, if I just want to get rid of that, I can recompile. And I can just run it and see that it works. Boom, nothing blew up. Great. I know my code works. That's all it is, but it's, notice I did a little bit at a time. Compiled, checked, compiled, test. I didn't even write the min factor function until after I compiled it one time, made sure that worked. Then I filled it in. Then I compiled and I checked. Over and over again. Just keep on compiling and checking. The worst thing you can do is write all your code all at once and then check to see if it works. It is the kiss of death, and I've had more than enough students tell me that they've done it when I finally probed enough. They go, oh, well, I wrote all of my code, I was pretty sure it worked, and so I wrote code for 5 hours, and then I checked if it compiled. No! Compile early, compile often, right? You have to build up. Don't just sort of ballistically write everything and then check if it works. All right, so that is Visual Studio in action. I have to go back and fix my slides for the previous example. So for Windows programming, by the way, we are doing Windows programming. We will do mostly console applications, but later on we're going to do some graphics window applications just for a little bit of a change of pace. So it gets a little quirky because most console applications, they're universal. You're writing on a Mac, you're writing on Windows, they have the same commands. For graphics, it's very different commands. Every single operating system is radically different. And so there are ways around that, but most of the time you have your own thing for each operating system. We've looked at C functions. We have an in, what's the input, what's the output, what's the name of our function. So something like, here's foo, it has two inputs, char A, char B, the output is int. Notice this thing is wrong. I need to return something. I need to return whatever my value is here. And I would get rid of this again late next time, right? I want to make sure that I point out what the problem is. Intentional problem, by the way. I need to return. And it has to be a number because of this. Right? That's the kind of thing we're looking at. I like to beat functions to death, so if you've already heard this spiel, I apologize, but I like going over it again. Functions themselves, I like proposing different ways of looking at functions just because to get one of them is going to fit for most people eventually. I like to think of functions like car parts, one of my metaphors that I go with. So normally, if I'm talking about a car, you would never just say, yeah, a car is just a whole bunch of stuff together. It's a bunch of iron, right? No, there's a bunch of parts. Each of those parts hook onto other parts. They all work together in concert. The car itself encapsulates a whole bunch of these little things, and each part does its own job. That screw holds this thing together. That engine is actually what's driving everything. The tires are what's keep that roll on the ground to help you transport. The idea of a car, though, is if I'm building these various parts, I don't want to worry about interaction. I want some input, I want some output, I want to have something to describe what that thing does. The tire spins, right? It rotates around on an axis and allows the car to drive. If you had some weird interaction effect, for example, if you honk the horn and your window went down, get a new car, right? That is like you would never expect that. Why? Because the horn does one thing. It makes a sound, right? It does not have a whole bunch of weird interactions. The idea of a function, and when we talk about objects, we'll get to the exact same point again, is each part does its own thing, knows how to deal with itself. I don't want my function to do 20 different things. I want it to do one thing, not a whole bunch. And I compose based off of these little parts. Each little widget, doohickey, doodad, does one thing, and you string them together, and you get sort of emergent or more interesting behavior. Each of the parts become part of a larger object, and if you keep it simple, that's KISS principle, keep it simple, stupid. Everyone's stupid. Every time you try and overthink things, this is my problem always, right? I overthink it, I try and do too much at once, and it bites me later on. Keep it as simple as possible that it does its job and nothing more, and then take other parts. If you start getting all cutesy, it's going to bite you later. Okay, more importantly, if I design a wheel correctly, I want to make it once. I want to make that design once. I don't have 4 different types of wheel on my car. I got 4 wheels. They're identical essentially. Each bolt looks about the same, or a bunch of the bolts will look exactly the same. I want to be able to reuse a design. It would be stupid not to, right? So my function allows me to do that. Notice I called find prime or whatever min factor. I called min factor a bunch of times. I didn't just replicate that code everywhere. I wrote the code. I wrote it once. I wrote it correctly once, or when I got it correctly, I had to fix it once, right? I had that for loop where I had a mistake in it. And as a result, when I fix my for loop, I fix it one time. If I duplicate my code, I got to fix it 5 times. If I had the same code a bunch of places everywhere, just duplicated, I'd have to fix my code a bunch of times, not once. So it allows you to reuse code, make sure it's right, and fix it in one place. Uh, User input and output is the exception, not the rule. Notice my function did not call printf once. It did not call scanf once. Most of your functions, 99.99% of the functions you'll write, if you ever write real industry code, will not have a printf statement or a scanf statement. It is the exception. Most functions have some input, they have some output, and that's it. They are not getting user input each and every time. User input comes in one place, and then a bunch of stuff happens. So, when I was making my video game, for example, you have mouse input, you have keyboard input, you have the mouse, you have the user do some stuff. That is a small fraction of the code. I had thousands upon thousands of lines of code, hundreds of thousands of lines of code that were doing nothing involving user input whatsoever. And then we had functions that were painting to the screen, like drawing stuff on the screen. There was no user input for that, but it displayed something on the screen, fine. But vast majority of the code was just the logic of the game. No input, no user input and output. Right? There was no, you couldn't put things to, you couldn't do a printf statement. If you had a printf statement on your paint method, so my paint methods were calling about 60 times a second. So if you're talking of like a video game, the frame rate's normally 60 frames a second, if not higher. So 60 times per second, the entire image, the entire scene, everything that in your game is drawn. 60 times a second. Any slower than that, any slower than 30 especially, it's actually, people hate it. They get very, very upset when you start seeing lag. So 60 times a second, everything is being drawn. And now imagine a printf statement at 60 times a second, even just one 60 times a second. What would happen? I'd have thousands upon thousands upon thousands of printf messages popping out onto a console window. You wouldn't be able to use it at all. So printf statements are the exception. Okay. I'd also like to point out, if I'm looking at the engine and I say the bolt is broken, what do I mean? What bolt? There are thousands of bolts in a car. What bolt am I talking about? And that leads us to the next part, the next metaphor for functions. The bolt I'm talking about is where I'm looking. If I'm talking about a variable called x, I meant whatever function I'm looking in, that x. I can resolve ambiguity because it's based on where I'm looking. If I'm looking at the engine and I say the bolt is broken, it means the bolt that is in the engine, and that's where I'm looking. I'm not looking in where the wheels are. I don't want to look at the tires and see the bolts for the tires. I'm looking at the engine, so the bolt that I'm referring to, probably the bolt for the engine. I had an ex-girlfriend many, many, many years ago. One of my favorite quotes of all time. Her quote was literally this: "Oh my God, something happened to something over there." She didn't point, nothing. My back was even turned towards. Something happened to something over there. What? Right? You need to have context. You need to be pointing at something. You need to know what you're referring to. Otherwise, it makes no sense. So when we talk about variables, it's context. It's based on where we're looking right now. So if my function has a variable, it's the variable for that function, not some other function. And that's an important. I can have multiple variables called x in multiple different functions, and it's resolved based on, I'm looking at this function. So when I say, variable x, it means variable x for that function, not for some other function. Okay, here's the black box metaphor. This is one of my other favorite ones, right? I have a function. Stuff comes in, magic happens, stuff comes out. That's it. Notice another key part. Only numbers or data moves. You never pass variables. The actual, the buckets that are storing these values never move. Just the values are moving. The values go from one place to the function and then go back out again. If we go back to, let me see if I can, let's keep that. Let's go back to this. min factor. I'm going to have a brand new variable called 2-factor. Every time I call min factor, I will make a brand new variable called 2-factor. It will be set to the value that gets passed in. The 7, it will say, okay, I'm going to make a brand new variable called 2-factor. What's the value going to be the first time? The value is going to be 12 the first time. The next time I call the function, I'm going to make a brand new variable called 2-factor. And what's the value going to be? It's going to be 7 the next time I call it. I'm going to make a brand new variable called 2-factor. And that's the value going to be? It's going to be 25 the next time I call it. The data, the values 7, 25, 12, that gets passed, but the variables do not. So I can pass in, let's just do this, factor 1. I could put factor 1 as this. The value for factor 1 gets passed here, not the variable. The variable stays where it is, just the value gets passed. So I want to do 7, right? Okay. And when I'm done, I return an integer, not the variable 2-factor, just the value being stored. I will pass back out a 2, not the variable 2-factor, but just the value 2. Data moves, not variables. Okay, that's important because of the life cycle of how a function works. So here's the life cycle of a function. First up, I make my new function. All my parameters, all my local variables, all the variables that are declared in that function are born. Pwang! And all the parameters, all the parameter values are set, but they're also created and they're set. So all those things in the parentheses, like 2-factor, are created then. They're made at the time when the function is called. They don't exist outside of that function. I call that function, I make brand new variables, and I set the values. Brand new variables each and every time I call the function. When I'm done with the function, we'll see what happens when I'm done with the function. Okay, so I make a bunch of variables. I do a bunch of work. The reason I chose rice picking, I figured, what's the hardest, nastiest, like tough work? Rice picking is a pretty tough job as far as I understand. Everything from the parasites that grow in the water to just the amount of manual labor. I figured it's a hard job. Okay, so the function does a bunch of work. So working in the fields, it's doing a lot of heavy lifting. It's doing a lot of work. And then when it's done, they all die. Every single variable just gets cleaned up and destroyed. They don't exist afterwards. And then for any of you that actually know what this image is, maybe you can think about it for a second what this image is. The parameters die, much like this man died. But this is from the movie The Da Vinci Code, right? In his death, this guy is sending a message. That's what's happening with our functions as well. You will pass back out information. In your death, you are passing back information to your main functions or to some other function. The variables die, but you can still pass messages back out again. That's why the life cycle of a function looks like this. You don't keep those variables around. They're born and they die within that function, and that's it. But message information can be passed in and out of those functions. Hence the life cycle of a function. By the way, the reason I chose that first image, I needed a baby being born and the word hello world because that's a computer science thing, so I found that funny. Okay, so here we go, my function foo. I have a variable x, a variable y. Notice I fixed foo. I have a variable x, a variable y. X and y are created when the function is created. And then I'm going to add two numbers together. I'm going to make a brand new variable called sum when this function is called. Sum is going to be equal to whatever x plus y is. And then I'm going to return the value that sum is. So what does the code above do? So let's say that this is in my main method. This right here, the x is equal to 4, sum, that sort of thing. What happens? So I have a variable called x that's equal to 4. I am then going to call foo. I can't resolve this sum thing until I call foo. So I'm going to call foo with the first variable having the value 23, the second variable having the value whatever x is holding. Oh, it's the value 4. So so I'm going to call foo with 23 and 4. So this variable here has a value 23. This has a value 4. This x is different than this x. This x is a different variable. I have two variables, both named x, and they're resolved because I'm looking at a function foo. The x I'm talking about is the one where I'm currently looking, not the one over here, not the one down here, the one up here. When I'm dealing with the function foo, the x I'm referring to is this x right here, not this one down here, this one right here. It's going to be born right now. It's going to die right here at the end. And that's it. The sum is equal to the value is 23, the value is 4, right? We said it was 4. Okay. And so the sum is going to be equal to what? 27. If my basic arithmetic is right. This whole thing, you could say, is exactly the same as just saying the number 27, right? Foo will return a value. Its value will be the value 27. You can just swap out the word foo 23x and just plop in the number 27. 27 plus 3 is equal to, a brand new variable named sum. Not this one up here, this one down here. They are different variables, this one and this one. They have the same name, but one exists here, one exists here. Okay, 23 and 7, this is 30. The value of sum right here, this sum here, is the value 30. The value sum when I was finished this function was the value 27. I can have variables with the same name and it gets resolved based on where I'm looking. This is why I want to make sure that you feel comfortable with this. I can have the same variable a whole bunch of times. Maybe don't, but you can have that because of how the life cycle of a function works. Okay. I also like, here's my third metaphor, baking and Legos. So this, by the way, strawberry cheesecake cake. It is a cheesecake with strawberry cake on both sides with cream cheese frosting on the top. Yes, it is as big and as heavy as that looks. My wife made it for our family and our neighbors. She sliced off the smallest possible slice for each individual person, and not a single person finished their piece of cake. It was a wonderful cake, but it was just a brick. It was just so rich. It would just kill, like, all of us were like, oh, I'm so full. I want to eat more. Cannot. Okay, neither here nor there. You can make it if you want, strawberry cheesecake cake. The key thing to it, though, is it involves making a cheesecake. It involves making 2 strawberry cakes. It involves making cream cheese icing with strawberry sauce on it and slicing up strawberries. That is not light and easy work. It requires a lot of complex steps along the way. Just making a cheesecake alone is complicated enough, and you have to do all of those parts. But making the first strawberry cake and the second strawberry cake is the same thing. So what I want is reusable code, things that I can do over and over and over again. In fact, for that cheesecake, I want a recipe for making a cheesecake that I can apply for this, or for making a maple cheesecake, or for making an Oreo cheesecake, or making something else. I want reusable stuff. So I want to break complex things into small little parts. I want to be able to, each part may have subparts. Making a cheesecake involves beating, then it involves the cooking, it involves mixing all the various ingredients, it involves this, it involves a bunch of steps. And breaking down big nasty problems into little minimal steps is itself an art form. So you're trying to minimize, that you don't have to wait. You can do the cheesecake at the same time as the strawberry cake. If you have to wait for one to the other, it's considered a worse solution. It's harder to deal with. The ideal solutions are the ones where they're not dependent on one to the other. You don't have to wait for the strawberry cake to be done before you make the cheesecake, for example. Okay? And the instructions and the items, how you do things, are based on the context, where you are currently in your process. Same with a function. I want little parts that do their own thing that I can reuse over and over and over again. I want something that can sort an array of items. irrespective of what's in the array, just sorts an array of items. I make no assumptions about how the array is actually working. I want, we're going to get to linked lists. I want linked lists that can take any kind of data you want to put in there, irrespective of the kind of data that you have, right? That's the kind of thing that I want. Reusable stuff. If you look at the Death Star from Lego, Legos are a great example of this, right? It is a whole bunch of really minuscule, simple pieces all strung together, and you'll notice even within that, there are patterns within the small pieces to make simple but larger pieces in there. And you do these patterns over and over and over again. If your Lego Star Wars thing with 4,016 pieces, if that Lego Star Wars, the instructions was just a little message that said good luck in it, then there's no way in hell anyone would be able to do it. It's, you need a bunch of instructions and you want these little parts that you build up to. If it was one giant instruction booklet with 4,000 instructions in it, you would not be able to do it. You wouldn't know where to go, right? You want little parts that you build on, and the functions then can call other functions. You can put the functions together. That's, it's breaking down big problems into small little chunks, like baking, like making a Lego set. And if you put it all in one function, you're doing it wrong. And I will call you out on it. Because it means that there's no way the TA is going to understand it. If you tell us there's something wrong with my code for the assignment and you give me one function with everything in it, I'm going to ask you to redo it again. I won't be able to understand it. It's too much all at once. You break things into small little parts. That's how you have to deal with things. And it's not my opinion, it's just, it's for your own sanity. Okay, so that's functions. Let's go to pointers and arrays, because I know this is confusing for a lot of people. So this, by the way, in case you're wondering what the heck this is the storage container that we were using when we were moving from Boston. So we had all of our stuff, or half our stuff, from our house in Boston that we had to put into storage for staging our house so that we can then move here. Notice we have all these boxes, and every one of those boxes should have some kind of number on them. This will have a number on it, this will have a number, this will have a number, this will have a number. My wife is extremely organized, and she had a spreadsheet with all of the boxes, the box numbers, and what was in each of the boxes. So if I want to find my pair of dress shoes, what box is it in? It's in box 57. I go to box 57, open it up, take out the dress shoes, right? It's still a search, but it's a whole lot better than, it's somewhere in there. If you're trying to find a pair of dress shoes in this without any idea what the boxes had in them, you'd go nuts, right? That's the idea that we're talking about with pointers. It is, I got like an array that we have a dynamic, make a dynamic array. It is a whole bunch of storage, but I need to know where I put all that storage. That's what a pointer is. It's not the actual contents, it's where the box is located or where the items are located. So the values that I'm storing is not the actual storage. I have a bin where I'm storing stuff. I can put values in the bin. That's what my variables are. It's a bucket to store values. And my functions normally only pass values and numbers. And they pass values and numbers only, quote unquote. We have addresses. Every single one of those bins has an address though. So I may have a bin like this. It has the number 42 on it because, you know, the meaning of life. And then it has some address in space. So 1, 2, 3, 4, 5, A9 or something like that. I don't know what that number is. It's some address. In space, somewhere on your computer, where this chunk O memory is on your computer, it is an actual address, like your home address. It's not your house, it's where, but you can pass the address of your house so someone can find your house. So when I make an array, I have a particular address for where all that memory is, and I can find stuff. If I want to get the address of something, I can put a circle, I can put an asterisk in front of it, and it says, tell me the address of this variable. So let's call it int my var is equal to 42. This is my var, and int this thing is just the address, this number, for my var. where my var is located in space. That's what that and means. If I put a star in front of it, it means instead of the pointer, go into the box. So I'm saying in box 42 are my dress shoes. The star means open up the box, get the dress shoes, right? I can go into the individual place. We have the square brackets. This is what we've been using with arrays. So I have an array, let's say values 0, 1, 2, 3, 4, 5. I would say give me whatever the address is. So I'll probably have a better example in a second. But let's do it is what is in the box at position 2. If I said my array plus 2 instead, it is the pointer to this. It is not the value in the box. It's not like, say, the value 4. My array at position 4 is equal to the value 4. My array plus 2 is the pointer to wherever the hell this thing is in space. It gets really kind of funky that way. If I use the arrow, it's the same as the pointer. This is the equivalent of, and this thing here is the same as when we use a dot for a structure. We'll see dots and arrows a lot soon. So when we have a pointer to something, using this is the same as a dot. So we'll see this in action very soon. So just keep in mind, this is effectively the same as the dot when we're using a structure. Okay, so our pointers point to a particular address in space. The pointees are the things being pointed to. So this is the pointee. The pointer is a thing storing the address in space. So my var is, let me see here. This, if I made a pointer to this, the pointee would be my var. The pointer would be whatever variable I put in there. And I like this as sort of as a metaphor. The cup is not the content. So if I have a cup of water on a table, you do not know what's in the cup. You're presuming it's water or it's coffee or whatever the case is, but you don't know. A pointer just says there's something over there. It's not what's in it. You do not know what's in it. You're just saying there's something over there. So the cup, if I said point to the cup, you'd point to my coffee cup, let's say. You do not know what's in the coffee cup. You're just pointing to the coffee cup. You do not know what's in it. If I wanted to get what's in it, I pick up the coffee cup and look inside. So that's when I would use this value right here, this star thing, the asterisk. If I need the values, I can then look into it. And if I don't know what I'm pointing to, or I don't want to point at anything at all, I use a null pointer. The null pointer is technically the value 0. It is technically the value 0, but you don't want to use the number 0. You want null. Why? Because you want to be very, very clear. It's not a mistake. You didn't accidentally do the math wrong. You're saying, I am not pointing to anything. It happens to be equal to 0, but I want everyone that reads this to know I'm intentionally saying I'm pointing at nothing. So if your pointer before was pointing at my coffee cup, your pointer now is pointing like at the ceiling, right? It's pointing at nothing in particular. Or you close your hand, or whatever the case is, right? A pointer that is pointing to null, it's a safe way of saying I'm pointing to nothing. Because how else do you know when you're not pointing at anything in particular? It could be some other legitimate address. You don't know. So we need some way of clearly saying I'm not pointing at anything in particular. I'm pointing at null, the value 0. So a null pointer is, if I have a pointer and I want to make sure, if I didn't set it up at all, I want it to always point to null. Because I want to make sure I know that it hasn't been set up yet. We'll do a lot of null pointers soon as well. So if you don't know what you're pointing to, you point to null. It's just a safe way of doing things. Okay, the the ampersand and asterisk things is a massive pain. This just requires a lot of practice. Anyone that's done my 1400 class has done much of that practice, but everyone else, you just do a bunch of examples just to make sure you get a feel for it. So the and again, the ampersand means it's a reference. So here is pointer 1. It is pointing to whatever my num is. So here's the variable my num. It's a bucket with, I'm going to put the number 4 in there again. Pointer 1 points to the address where that is. Wait, we can even do, so we'll have an address, whatever that address is. It's the address of where this thing is located. We can also have pointer 2, which points to pointer 1, the address of pointer 1. It's not the address of this, it is this points to this points to this. So I can actually do a bunch of these things in a row. So to get to my num, I do star. So instead of pointer 2, I go, so here we go. Star pointer 2 says, what's here? The contents of this squiggly line here. Okay, and I would put another star in front of that. It says, what are the contents of this? Oh, it's this value 4. This would be star star pointer 2 is equal to 4. It is not this. I walk one step in and I walk another step in. That's what the dereference means. It means go to where go to where the address and look at what's inside. Go to the address and look what's inside a bunch of times. Okay, so here is an array. I want you to find numList 3. So that is 0, in this case, what is the value? 0, 1, 2, 3. That is the value for it. It's not the number 3, it's a value 4 right here. I want you to get the equivalent of that as a pointer. And I want you to get 2 equivalent ways of getting that value. So I want you to try this out because it actually ends up being kind of interesting. So numList plus 1, by the way, is this value 2. It points to this value here. So if I said that is exactly equivalent to 2. It is, I'm pointing at this first, numList points to the beginning of the array. I add 1 to it. I'm now pointing to this element of my array. I dereference it, and instead of pointing to the address in space, I'm actually getting the value inside, which is the value 2. So can you come up with 2 different ways of getting the exact same thing as this? In fact, I want you to do one step further. I did this in the BIT2400 class last term, and you guys, they did, the students in that class, if you're there, I was very proud of how awesome some of the ridiculously crazy examples you gave me were. I loved it. Great work. I want you to come up with the craziest thing or one of the more crazy ways you could write that. There are 1,001 ways to get this value here by referencing and dereferencing, because you can always reference and dereference a bunch of different times and add 4 and minus 3 and whatever you want to do to get the exact same value here. So try at least 2 ways of doing the exact same thing as this, and then try the craziest thing you can come up with. I'll take a pause of the video, try this out, make sure you are feeling comfortable with this, and then we'll move on from there. Okay, I'm hoping you tried it. I'm hoping you stayed comfortable, or you were feeling comfortable with this. So let's see if I have a couple of them. I don't have a couple of them here. Let's try some. So numList of 3. So what could I have done? I could do numList plus 3, which would be the pointer to where that 4 is, but not the value 4. And then I could put a star in the front. That would be the equivalent. I could do, let me see here. Plus 2. plus 1, and then put a star in front of it. This is the same thing. It's going to be effectively the same thing. I'm going to point to this one right here, the 3 right here, pointing to this part right here, and then I'm going to add 1 to the pointer. It's going to point to this thing right here, and then I'm going to dereference it. Let's do something crazy. So num list plus 4, just to be stupid, and then put a star in front of it. That would be the value 5, and then I could put an asterisk in front of that, and then I could plus, minus 1. That will move it back 1 space, and then I could put a star in front of that. And my parentheses are probably wrong, but let's just pretend that they're right. All right, that's also something crazy. That would do the same thing. It's pointing to the 5, then moving it back 1 space. I go to the 5, get the value 5, I get the pointer to the 5, then I decrement it by 1, so I move back 1 space, then I get a pointer to, then I find out what the value here is. I dereference whatever that what I was pointing to before. I could do num list of 1. That would be this value 2. I could then say, get the pointer to that, plus, I want to do 3, right? So plus 2. So it would be getting the value at this position, the value 2, dereferencing it so you get the pointer to that 2, then increasing it by 2 to getting the pointer to this position here, and then getting the value here. I could do numList 1, put an ampersand in front of that, and then put a 2. That's also going to do the exact same thing. This is going to be exactly the same as this, right? This square brackets parentheses thing is just shorthand for move it over a certain number of spaces, get what's in the bucket, right? Not get the location of the bucket, get what's in the bucket. Play around with this, get a feel for why all of this stuff works. I wouldn't expect you to write stuff like this ever. It would be terrible to write stuff like this. But if you can do some of these crazy drills, it means you really have a good sense of dereferencing and referencing, because it will get very hairy when we start dealing with objects. You'll have pointers to pointers to pointers to pointers to reference to pointers to data. When we do linked lists, we're going to be dealing with pointers. It will get hairy. Okay, so I want you to feel more hopefully comfortable with this. The idea is what I'm pointing to and the value are different things. The address where it's stored and what's what's at that address are different. And I want to be able to go between the two. This is very unique to C and C++. So you may not see it in Python, but it's everyone that does C and C++ has to know this sort of thing. So, by the way, in case you didn't know, C now allows you to do this. I said you only pass in values. It turns out that's the one weird exception that you can do. I can pass by reference, which means if I change my num, I will change. So I have foo, some variable. If I change my num somewhere, variable changes as well. I pass the pointer to that value, and I can modify this thing here. It is something we're going to be playing around with in the lab. Or I can just pass a pointer to the variable. Because it's a pointer to some variable, it's a loophole. I'm only passing a value here. That value happens to be the address of a variable, the location in space where a variable is like var. So if I pass the pointer to var, what ends up happening? If I change my if I change what my num is pointing to, so here is var. I'm pointing to whatever the variable is. Let's say it's 6 now. If I then say, let me see, dereference my num, let me rewrite that. If I dereference my num and that's equal to 8, it means I can go to my original variable that was calling this function foo and stomp on and put in a new value. I'm passing the address. If I pass you my address, it doesn't mean I give you my house. It says I give you my address to my house. You can now go to my house and rob me. Right? That's why I don't give you the address to my house. So the idea is if I pass a pointer, I can then go to where the address is and stomp on original data if I want to. It can get really complex, so take your time. Make sure you test your code as soon as you write something with a pointer to make sure it's working before you move on. And don't get cutesy. By the way, anyone want to think about, I pointed this out I think in 1400 before, but what's potential issue with pass by reference? As in, I call some function foo with some variable, and then if I change my num, I will change the variable. So what is potentially wrong with that? Well, the issue is nothing has told me when I'm calling foo, no one has given me a warning that foo can change my original variable. I assume it never does change the original variable, and yet it can. If I'm passing a pointer, I know someone can mess around with my variable. But if I'm calling by reference like this thing does, I can change my variable. The other function can change my variable without me being aware that it's doing that. And that's going to be a problem because you don't know if somebody else is messing with your code or not. It's one of those issues. Okay, we're going to do some malloc and free, but then we're going to revisit a lot of this stuff again. So last time around when we were in 1400, hopefully you guys never did new because that is not C code. That is C++. So here is what we did in the past for making an array, a dynamic array of variables. I said, okay, I need an array of integers. So I want to get, hey system, give me an array of 17 integers. How big is that? Well, it's the size of an integer multiplied by 17, meaning if I have 17, let's say this is an integer, and it will keep on going dot dot dot. But I need to know how big this thing is because this is how many bytes of data I'm going to get. It is essentially 4 bytes of data per integer multiplied by 17, 17 times 4. That's how many bytes I'm going to get. This will give me how many bytes of data I get from the system. And then I say, no, 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 it's a pointer to an integer. So it is pointing to this thing right here. The only difference between a pointer and an array is effectively there is no difference. The array is a chunk of memory and you can move around within that chunk of memory, but you have no way of knowing if it's a single variable or it's a whole lot of variables one after the other. That leads us to why I name my things like this. This is my convention. You do not have to follow it. This is how I do things. But if I don't know if something is purely a pointer, I'll put a P at the front. And if something is purely an array, I'll put an A at the front. Meaning this is an array, treat it like an array. You need to delete the array later, that sort of thing. If I pass something in and it's supposed to be an array, and you can't tell if it's an array or a pointer. So having this little a underscore as part of the naming convention just lets you know it's not just a pointer, it's an array. Okay, so I get this giant chunk of 17 times 4 bytes of data, and then I point to the very front of it. That's what malloc does. Give me this giant chunk of memory, or this, not giant chunk of memory, but this chunk of memory, and a pointer to the front of it. And then I say that pointer to the front of it is an integer pointer. And so now if I plus 1 to it, I get to the next element. Plus 2, I get to the next element. Plus 3, I can walk around in my array. That's malloc. New is a nicer version of it. I love new. It is nice, or at least I like it. Here's what it looks like. Same as last time on the left-hand side. It looks exactly the same. Except instead of having to do casting, instead of having to do size of, I just say, give me a new array of integers of size 17. Done. It's really nice, right? I want an array of integers, the array is size 17. This makes sense in terms of syntax, at least it does to me, right? Give me 17 integers. Okay, when I'm done, if I'm doing malloc, I call free. I free this thing. If I'm using new, I want to call delete. It's just you have something that matches. So I call delete. if I'm deleting an array, I need to include these square parentheses. If I don't, it's just going to think it's deleting an object. That's a whole other thing. So for deleting an array, if I have an array, I need to put the square parentheses here. In case you think that it's not a common problem to forget to include these square parentheses when you call delete, when I was making the assignments and the examples last fall, I had bugs in my code when running my code because I kept on forgetting to put those in there, just little typo errors. And I had to track them down and find out, oh, whoops, I called delete on just what I thought was an object instead of deleting an array. It happens. Everyone makes little, syntax errors. But I made those syntax errors just last year. I make them all the time. So when I call delete, if I call new, I call delete, but I also need to make sure I put these square parentheses in there. All right. So what I might do now is just take a brief break because that's a lot to take in. Make this your own. Make sure you understand how to do this. Make a couple arrays. Make a couple arrays with new. Make a couple with malloc. Make some pointers. Move around things with the pointers. Code something up. Just get a feel for it to make sure you're comfortable. Because I guarantee you, the next assignment like our first major assignment, there's going to be a lot of this kind of stuff. Okay, so let's take a quick break, and then when we come back, we'll look at preprocessor directives. All right, thanks everyone. This.